Let's talk about some of the properties of integrals. We'll step through these one at a time and give little pseudo explanations for them. Let's start out with some setup. Let f and g be integrable functions on an open interval that contains the points a, b, and p. Okay, property 1. The integral from a to a of f of x dx is 0. Well, this is technically by definition, so there's not a ton of explanation for it, but there kind of is, right? If you imagine a function, here's our f of x, and we're trying to compute the area under it from some region, from A to B. But what if instead of going from A to B, we just went from A to A, right? So what's the region under the curve enclosed by this little rectangle with a base that goes from A to A, right? There's no area in there. A equals 0. So what could the integral be? Well, it must be 0 since the integral is the area under the curve. So that's kind of intuitive. But really, we'll just take this as a property that's given by definition. Okay, on to property 2. This one comes in very handy, but there's not really a geometric way of thinking about it. So we'll just take this one as a definition as well. Once we get to the fundamental theorem of calculus, you'll see why this really makes sense and why it's super useful, and it'll kind of fall into place a little bit. But for now, let's just take this by definition, that the integral from a to b of f of x is the same as the negative of the integral from b to a of f of x dx. On to number 3, this tells us that the integral of f plus or minus g of x, well, it basically tells us we can break up those integrals to the integral of f plus or minus the integral of g. Well, this one follows from the limit definition of the integral. Recall that the integral is actually the limit of the sum of a bunch of little tiny rectangles that are very skinny, and we add them up and we let them get smaller and smaller and smaller. But this plus or minus property of two functions inside of something happens to be one of our properties for both sums and for limits. So it makes sense that it would also hold for integrals. So that's essentially where that property comes from. Same thing with property 4. This one tells us that the integral of a constant times a function is equal to that same constant times the integral of the function. So what's really happening here is this constant c is coming out to the front of the integral. But we've also seen that as one of the properties of sums and limits. So it would make sense that the c comes from inside the integral out to the front. So property 4 there again comes from the limit definition of the integral. Property 5 we can look at more geometrically. Let's imagine a scenario where there's a function and it's defined on some interval from a up to b, but there's some p in between here. So then the integral of the function from a to b will give the entire area under the function, that is between the x-axis and the function, between a and b. But if we wanted to break it up, note that we could, and we could integrate just up to p first and get this small area here from a to p, and then get this second area from p to b. Same thing for the second area over here. That would be the area from p to b of the function dx. And then note that the total area would just be the sum of a1 plus a2 here in this little illustration. So we can stop at some point between a and b and just add those two areas, or we can just go from a to b. The weird thing is about this property 5, it doesn't actually say anywhere that p has to be between a and b. So you can take it literally up to a point with this geometric argument, but mathematically there's a lot more that goes on with it behind the scenes than what I'm showing in this geometrical argument. Let's look at property 6. That was a little longer here. It says the function of the absolute value of f is integrable on the closed interval ab, and that integral from a to b of the absolute value of f of x dx is the sum of the regions bounded by the graph of f and the x-axis on the closed interval ab. Ooh, that's a lot of words. Let's draw a picture. That's a much better way of understanding mathematical entities. So let's just look at a function, and then we'll look at the absolute value of that function, and that'll become clear. So here's a nice function, and let's integrate it. Let's look at the area from, let's say, a up to b. We'll call this f of x. We'll recall that the integral gives what we call the net area, which is essentially the region under the curve or between the curve and the x-axis. So we have this would be positive, and then this area down here would be negative, and then we'd add this area up here going up to b, that would be positive again. So that's an interesting area, but it's not exactly what we always want. Sometimes we want just the actual area between the curve and the x-axis without all this negative business going on when it's below the x-axis. So for that, we just take the absolute value of the function. So I'll draw that in. It'll be the same function, except for before, where it was negative, the absolute value pops that up to the positive version of it. So now we have positive, positive, positive of the three regions. So now we can just get the total area between the function and the x-axis without having to worry about the area below the x-axis being negative. So if you're working with geometry, taking the absolute value of a function is a great way to compute areas without having to correct for negative areas. Okay, here are three more properties of integrals. And I know all these properties seem like a lot, but these are what makes the integral so useful, is that there are so many ways we can manipulate them and work with them, that they really become one of the most fundamental tools of all of mathematics, because they're just so versatile. So let's check out these new properties. Now we have slightly more restricted conditions here. Let f and g be integrable functions on the closed interval a, b. So that's slightly more restrictive than the previous conditions, but not that big of a change. Okay, the first one says if f of x is greater than or equal to 0 on the closed interval a, b, then the integral from a to b of f of x dx is greater than or equal to 0. Well, let's visualize this. If you have some function f of x that's integrable over the closed interval a to b, and you just think of this area, well, the function here, note that this function is greater than 0 everywhere, at least between a and b. And because it's above the x-axis, that's always going to give us a positive area, because the integral gives us the net area. And because the area is always positive, the integral itself is going to be positive. Thus, we can say the integral is greater than or equal to 0. So that one has a nice geometrical argument. Moving on to property 2, that tells us that if f of x is greater than or equal to g of x on a closed interval a to b, then the integral of f of x is greater than the integral of g of x. Well, that one too we can gain an intuitive understanding of, though it does get a little busy on the same graph, but let's take a look. Well, we'll say f of x is bigger than g of x everywhere on the closed interval from a to b. So we'll draw f of x maybe up here, a bigger function, and then g of x will be some smaller function, maybe down like this. Well, then note that on a to b, if we consider the areas under these two, look, the area under the red function, under f of x, is all of this. So that's clearly going to be greater than the area under the blue function, which is g of x. G of x, by the way, is this blue one here. Thus, the integral of f of x on that region will be greater than the integral of g of x on that region, considering that the integral gives us the area under the curve. For property 3, we can also use geometrical reasoning. It tells us that if little m is less than or equal to f of x, which is less than or equal to big M, then little m times b minus a is less than or equal to that integral of f of x on a to b, which is less than or equal to big M times b minus a. When you see this in symbols, it seems really terrible and slightly overwhelming, but when you see it in pictures, it makes perfect sense. So let's consider such a function. All right, there's a nice function. So note that this function is everywhere bigger than little m, which we'll write in down here. And note that that same function is everywhere less than some big N, which we'll put in up at the top. Okay, so this theorem works on functions that are bounded somehow, at least within the region from a to b. Well, then we might not know much about this integral, but we can clearly say that the area between it and the x-axis is going to be bigger than this rectangle here, made by the little m and the width just from a to b. Okay, this is only from a to b, so let's put up these limits here. So this area under f of x is going to clearly be bigger than this blue area under little m, but it will also clearly be smaller than this area under big M, which is going to just completely encompass the entire region here. So the area under big M makes a very big rectangle, the area under small m makes a very small rectangle, and the area actually under the function is somewhere between those two. Well, what's this small rectangle, big rectangle business? When we look at this little m times b minus a and big M times b minus a, those are just the rectangles. Little m is the height of the rectangle, and b minus a is the width. And same thing with big M over here. Big M is the height of the rectangle, and b minus a is the width. And of course, the integral gives us the area under the function, which will be between the areas of those two rectangles defined by the m's.